Hey everyone, Morgan here. We're on page 2 of the Thermodynamics lecture outline for AP Chemistry. And we're going to be talking about a concept today called entropy. And entropy has become a somewhat controversial thing to talk about in the last couple of decades because there are different ways for us to look at it. Now, typically, Wikipedia included, most freshman chemistry textbooks will refer to entropy as a quantitative measure of disorder, meaning we are measuring with a number the amount of disorder in a system. Now, the more specific definition and the more accurate definition would be to say that entropy is really a measurement of the number of different microstates that the particles in a system can exist in. That is something that I don't think is terribly easy to comprehend as a high school student. So the AP exam is still allowing, people to talk about entropy in terms of disorder or the ways you can assemble a system. Now for us, we're going to be using entropy to help us to determine the spontaneity of chemical reactions. And what we just need to understand, and I think this is pretty straightforward from your everyday lives, is that an ordered state is not generally going to occur spontaneously. You have to do work for an ordered state to occur. Your room does not just spontaneously clean itself up and organize itself. Okay? Can it spontaneously become messy? Well, we can debate that, but if you clean it well, close the door, go away for a year and come back, there's going to be dirt and dust inside the room. I don't know that all the books are going to fall off of your bookshelf, but it will become more disorderly. So I want to use the example of a piggy bank. Perhaps you're familiar with these. A piggy bank in my youth would have been made out of something like porcelain. It would have been a ceramic, and you put coins in it all year long. And then when you break it open to retrieve the coins, there's some different possibilities. Let's imagine we hold that piggy bank up in the air, hit it with a hammer, it breaks, and all the coins fall to the floor. Okay? When they fall to the floor, are they going to fall into stacks of dimes, stacks of nickels, stacks of quarters, stacks of pennies? I don't think so. What you're going to have is massive disorder. You're going to have a real big mess, a mixture of coins, and they can exist in many, basically an infinite number of different ways depending upon how many coins that you have there. Okay? Not stacks, and definitely not stacks where they have already separated themselves out by denomination: pennies, nickels, dimes, quarters. Okay? So what this is telling you is that disorder favors spontaneity, and we have developed a way to measure that. Okay. The name that we're going to put on that is called absolute entropy. And you might remember the term absolute from when we talked about temperature scales. Absolute entropies will never have a negative value. Okay? It is a scale of the entropy that a species inherently has. Okay? Whether that species be an atom, a molecule, a macromolecule, whatever the system is that we're looking at. Okay? What that individual species inherently has as its entropy. Okay? This is based on its structure and state of matter. The more particles that are in a system or in a species, the more entropy it's going to have. And by particles, we can be getting down to and talking about protons, neutrons, and electrons. So since this is a scale, we need a reference point. Okay, I can't just, look at a student in the front row of the class and say, how messy is your room, and have them say 7. It doesn't work that way. Okay, we need to know what to compare it to, a reference point. Now we're going to use the hydrogen ion, H+, at 25 degrees Celsius and 1.00 atmosphere of applied pressure. We're going to say that the hydrogen ion has 0 entropy, typically measured in joules per mole Kelvin. Okay? Now, as a reference point, this works well because the hydrogen ion is a single particle. It is just a proton. There's no electron present. It lost it. It's positive. There is no neutron present. Okay? It's just a single particle. And if you have a single particle, there's really only one way that you can arrange it, and we're not looking at a whole lot of disorder here. Okay? Now, we need to realize that temperature affects entropy. Generally speaking, an increase in temperature is going to cause an increase in entropy. Now, negative numbers. No, this is an absolute scale. Okay? Now, what we can see is when we talk about a change in entropy, you could possibly have a negative number. Now, entropy in general is given the symbol S, and we talk about S naught when we're at standard conditions, 25 degrees Celsius, 1 atmosphere. Okay? Delta S naught can be negative, but S naught can never be negative. That will always be a positive value. So as a general statement, what we will say is that the entropy of a solid is less than the entropy of the corresponding system if it were a liquid, which is much, much less than the entropy of the corresponding gas. So, if I have 1 mole of water in the solid phase, it has less entropy than 1 mole of liquid water, which has a lot less entropy than 1 mole of gaseous water. But that should make sense to us, because when we talked about a gas, we talked about how random and chaotic the particles are in a gas. And when we talked about liquids and solids, especially solids, we talked about how organized and orderly solids are. Okay. Now, very important to know that entropy is a state function. It's independent of path. And that means that we can find the change in entropy by doing products minus reactants. All we care about is the initial state and the final state. So for this typical chemical reaction, delta S naught reaction is equal to C times the entropy of species C plus D times the entropy of species D minus A times the absolute entropy of species A plus B times the absolute entropy of species B. And that was what we called products minus reactants back when we were talking about thermo in that chapter in the fall. Okay, that's everything for page 2. We'll continue this discussion on page number 3. This is Morgan signing off.